Okay.
Okay, I think now we're good to go. Good to go on Zoom end. People can hear me.
Yep, I hear you.
Perfect. So let's get started. My name is Stéphane Aroca-Ouellette, and today I'll be presenting my thesis, Word Human-Inspired AI, Data, Structures, and Hypothesis-Driven Learning for Greater Generalization. So let's start with why generalization is important itself. There are some very practical reasons. It reduces training costs because you don't need to retrain as many times for different contexts. It improves robustness because if there's noise or variations, the model should still be able to perform well. It also helps with scalable deployment because you can have a single model deal with a lot of tasks rather than having a model per task. But perhaps most importantly is novelty. Most of the most important things occur at the boundaries of knowledge and therefore don't really have training data to already exist. And this is where you really need generalization to be successful. Current AI, they're extremely prolific these days and can be incredibly useful, but they're not great at generalizing to new tasks. So this is a task from the Arc-AGI dataset. And it's currently a dataset, or version 2 of the dataset, where humans get 100% on the dataset, and the most powerful models, Grok 4 thinking here, gets about 16% accuracy. GPT-5, which on high mode, which was released just last week, only gets about 10% accuracy on this dataset. And it really goes to show that humans are still the gold standard in terms of efficient, adaptable, and generalizable intelligence. So how do we do it? How do humans generalize? So I'm just going to walk through an example of how humans may approach this task. At first glance, we identify the relevant data, right? So in this case, we can see that there's 4 clear different colors, likely indicating different things. We can also immediately look of like how they change between the start and the end state. And in this case, we can see that the green, for example, remains static in all cases. It's probably a background and not so important. The red changes, in this case, from red to black. And the black here actually seems to move from here all the way up here, which kind of delineates a rough hierarchy of what the importance of different objects, with the black being a movable object, perhaps being the most important, green and red being changeable, indicating some importance, and green kind of being a background. Now, this spontaneous movement and movement for no other reason kind of indicates from human priors that this black might be some kind of agent. And agents inherently have goals, which kind of leads us to believe that this red might be the goal in this case. And this kind of creates an initial hypothesis on how to solve this task. Now, if we directly apply this, we can test it in our other example. And you see that if that were the case, we'd have the black end up in this red down here, which doesn't actually happen. We end up with the black here, and therefore our hypothesis has to be wrong to some extent. Now, we had kind of indicated earlier that green was kind of static. Things that are static off in the background could probably indicate a wall. And that makes sense. We actually, again, identify the data that's different between our initial task and this one. We see that here there's a path that's too narrow for the wall to pass through. And so we can update our structure that we defined to incorporate this, where an agent moves through space to reach the red goal and is blocked by walls if it's too narrow. One second. So this is our new hypothesis. And if we go to our initial example again, this works very well. Sorry. Okay. And now if we test it across our other example, we again have a successful pass here. So we can actually test it on our full example, on our test example here. And if we do, we are successful on this task. Just going to run through a second example, although quite a bit faster this time. So again, we have a different task, again, from the Arc-AGI data set. And the first thing we might do is identify data. Now, humans have a strong prior about blue, and that it's often water. So we can build a structure around this. Water flows through space, which is black in this case, and it's blocked by walls, which can really be any color. And we can then test it against our 2 other examples, and we see, yes, this hypothesis holds true in all our examples. We can apply it to our test example, and again, we succeed. And so this thesis is going to explore how we can design more generalizable AI systems by drawing inspiration from the way humans learn, reason, and adapt. Now, in that explanation, something I brought up a lot was priors. And from a young age, humans can infer causal relationships from just a few examples. Over time, this builds a rich, diverse network of causal understanding. And I argue, along with some other researchers, that our capacity to generalize is built on this foundation of causal understanding. Specifically, this causal understanding provides the priors for us to be able to identify data, to build the right structures for the task at hand, which in turn form the hypothesis about our world, and we can use those to then update again our priors about the world. And with that, I'm going to go into an overview of everything I'm going to talk about for the rest of the presentation. So at the start, I'm going to talk about how humans use data in natural language understanding and highlight two papers, Proust and Reseed. You'll see these other two papers here. These are kind of supplementary papers that kind of aren't going to make the time cut of this presentation. But if you have questions about them, I'm happy to answer about it afterwards. The second section will be on structure in human-agent interaction, highlighting my paper HaHa or Ha squared. I will then be talking about hypothesis-driven learning in few-shot behavioral cloning with my paper Proj. And I'm finally going to finish off with what's next and what the future holds. There are some icons that are denoted here and a timeline at the top to kind of keep you on track of what's happening throughout the presentation if you get lost. And with that, let's jump into the first section, data and generalization, and how we can leverage the data sources that humans rely on. If I asked you how to predict how many people in Massachusetts will vote, but gave you American cheese consumption as your only input, you'd probably be able to make a shockingly accurate model. That being said, I hope none of you would go to the Democratic Party asking them to give cheese away for free. And this kind of correlation versus causation is a big problem in the way that current models learn. Because they have such predictive power, it's very easy for the models to just learn to use this to solve the prediction task that we've given to them. In this other case, we have a husky versus wolf classifier that was trained and very high accuracy in the training set, and the test set did very poorly. And when they looked into why, they realized that the classifier was just looked at whether there was snow in the background of the picture. And these kind of things are often deemed shortcut learning, right? They essentially are going to find the shortest path between what we're asking them to do. And if we don't provide the edge cases of why those break down, this is what happens. And humans, because we know what is important and which isn't, it lets us avoid issues like this, where a model can get fooled simply by adding a sticker with iPod written over it. So let's talk about natural language understanding. Human interaction with the environment, and it's been shown through quite a bit of research, is fundamental to how we give meanings to words. However, current LLMs are trained almost exclusively on text without any of this data. And so in this section, I'm really going to focus on how can we build systems that harness these signals that are so beneficial to humans. Which brings me to my first paper of the talk, Proust, Physical Reasoning about Objects Through Space and Time, which was published in ACL Findings in 2021, and is co-authored by Corey Pike, Alessandro Roncone, and Katarina von der Benz. So the motivation for this paper is to zero-shot probe the physical reasoning of language models. It consists of about 19,000 multiple choice questions using 14 templates and covering 10 physical reasoning concepts. The concepts are kind of broken down into 3 different sections. The first one is a standalone section on direction. There's an example of the right person is walking north, they turn left, which direction are they now facing? The second set of concepts are about the attributes of objects. So how can you compare the mass, height, or circumference of objects? So for example, if you have a seesaw and you place an object on both sides, how is the seesaw going to move? And the last one is affordances. So essentially, do specific objects have specific characteristics? Are objects stackable or breakable? Let's dive into one of these templates a little closely. So in this case, it's a template used to test the stackability of objects. So a person is trying to stack bricks, eggs, pens, grapes. The blank are the easiest to stack. In this case, bricks is probably the answer that most people would lean to. But I'll also highlight 2 other parts of this template. The first is that we can order the objects, the options in the question in any way we want. And I call this object order. The second is that we can actually ask the question in 2 different ways. We can either ask which objects are the hardest to stack, or which are the easiest to stack. Of course, we'll make sure that when we do this, we give a single object that is the right answer and 3 objects that are the incorrect answer. So I'm first going to look into these 2 kind of parts of the templates that I talked about, the object order and the superlative inversion. So object order, we see that language models do indeed have a strong bias about the order, heavily favoring the first and fourth object in the list, and really not liking to predict things that are in the 3rd position. If language models really understood the fundamental concepts, this wouldn't be the case. They would reason about it, and it shouldn't really much matter the order of the objects in the question. Similarly, for superlative inversion, if you're able to identify which objects are stackable, you should be able to identify which objects are not stackable. However, we can see this is the average accuracy difference of asking the question one way versus the other. And we can see that there's about an 18% difference, but depending on which way we ask the question, kind of again showing that they don't understand the fundamental concepts at play. Looking at the main table, so we tested a bunch of different language models in this paper, and we can see that the best result of the most of general models was Albert V2, and it only got about a 32% accuracy. Now, this is a four-way multiple choice. These are four-way multiple choice questions, so random chance is 25%. They don't do very well. Now, scaling is all the rage these days, so we also tested, does scaling help with this? If we just scale the models, will this eventually get solved? And we found that self-supervised models scale very poorly. The only model that scaled well was Unified QA, which was at the time, state-of-the-art question answering system that was fine-tuned on a lot of data, like specific data, and might actually overlap with some of the questions in this data set. So the main takeaway from approach is that physical reasoning does not emerge from text-only self-supervised training. This is one of the supplementary papers, The World of an Octopus, How Reporting Bias Influences a Language Model's Perception of Color, published in EMNLP 2021, co-authored by Corey Pike, Alessandro Rincone, and Katerina von der Vents. After that first paper, the two natural questions we had are, why is text training so limiting? And is there anything we can do about it? And the main takeaways from this paper were that one of the reasons why language modeling or text training only from language is an issue is reporting bias. Humans tend to omit obvious information from language, and inherently this limits a text-only model's predictive power about color. So the big example in this paper was yellow versus green banana. Green banana appearing in Wikipedia much more frequently than yellow banana, even though humans know that yellow bananas are typically yellow. The second part we did is that we tested CLIP, which was a multimodal model, and showed that using additional modalities in training can actually help us mitigate this limitation. I'm going to move on now to another primary paper of this presentation, Reseeding Latent States for Sequential Language Understanding, which is currently under review for EMLP 2025, and is co-authored by Katerina von der Vents and Alessandro Rincone. What can we do about this? The first two papers really investigated the limitations, but didn't propose a way to tackle it. And this is what this paper really tries to do. Now, you may have noticed that there's quite a few years between the last two papers and this paper, and in that time, language models have exploded. ChatGPT was in infancy in 2021 and wasn't really available to the public. So just as a recap, I'm going to walk over the current state of currently how LLMs are trained. In stage one, we do causal language modeling. And this is actually very similar to how language models were trained back at the time. The only difference is the scale. But the task here is really just to predict the next token in a sequence of words. It's good for capturing the linguistic patterns and world of knowledge from text, but not much more than that. Stage two, supervised fine-tuning. For language models to be useful, we actually really want them to be able to predict the next token in a response, not just generally out in the wild. And to do this, they perform supervised fine-tuning, which is essentially fine-tune on a curated data set of instruction and response pairs using the same causal modeling loss used in the first stage. And this really helps improve task following and formatting. The last step, which was a big breakthrough at the time, is what started ChatGPT really, is alignment through RLHF. So here they meant the instruction response pairs to have two responses per instruction. They then get a bunch of humans to annotate which response they prefer. You can train a reward model on this preference pairs and use that to fine-tune your model to be more aligned with the preferences from humans. There are some more modern versions of this, like DPO, that don't learn the reward model, but the idea is the same of like learning from human preferences. And these are great. They've really helped us create language models that are very useful, but they do have a lot of limitations. The first is scaling limits. A lot of the growth that we've seen is because we've just used more and more data. We're actually reaching the limits of the amount of high quality data that currently exists in the space. So we can't really just expect to keep scaling it. High quality data doesn't exist. In fact, we've already really blurred the lines of legality with the use of copyrighted data. The second, as mentioned, and kind of foreshadowed my earlier work, is text-only training misses key relationships. Text abstracts away spatial, temporal, and causal structures and omits facts that are self-evident to humans, as shown through reporting bias. And lastly, we do have this new data form of preference pairs. And while these are very helpful, they're also very sparse and subjective. One annotator might prefer the sentence that is more grammatically correct, even if it has small factual inaccuracies, or another might care very much more about the factual accuracy of the statement. It's also a very coarse-grained metric. You only get a single bit of information for 2 full sequences of text. And currently, LLMs struggle with compositional reasoning still to this day, planning and length generalization in sequential tasks. And I hypothesized that these limitations are the reason for that. And to address this, we propose that we need to use a third kind of data, and that's data from the environment. Again, human language is kind of built on interaction with the environment, and it's so crucial to us that it's odd that we would try to not use it in these language models. It also very much complements data and preference pair data. It preserves spatial and temporal relationships. It is concrete to fully specified, avoiding abstractions and bias, and it is dense, informative, and objective. While there is some work on existing ways to ground language models, there's kind of 2 main limitations. The first is that they either require a fully separate module to simulate the world and use the output of that simulation, which can be very useful, but it's kind of masking rather than addressing the limitations of our text models. And you're also at the whims of your simulation model. And everyone knows simulations are very difficult to do, especially when you get to more abstract tasks. The second one is implicit alignment. The second direction of research has been implicit alignment in encoder models. And this is during training, they try to align data that is aligned with things that we see in different modalities. And while I've taken a lot of inspiration from these approaches, there's 2 main limitations. The first is that we've realized that decoder models are just much more useful for a large range of tasks, and encoder-only models have slowly been a smaller and smaller part of the language modeling space. The second is that they don't actually create any explicit information to use at inference time, relying fully on just what's internalized in the model. So to this end, we propose reseed, refeeding state embeddings aligned using environmental data. Reseed is a method to ground decoder-based LLMs in structured environmental signals during training to improve their reasoning and generalization in text-only inference tasks. So let's see how it works. So in this, we start with a description of an initial state, and then a description of a series of different actions being applied to the initial state. We append a special state token after this description of the initial state, as well as after each action that is performed. We take the token from the special state and pass it through a state modeling head to create a latent state representation of the state. We then train this latent state representation of the state to match the real state through 3 different losses. So the first is to do this, we do need to train a autoencoder of the states themselves so that we have a ground truth latent state representation. So the 3 losses we use are a mean squared error loss between the latent state representation from the ground truth states and a mean squared error loss between the latent state representations generated from the ground truth states compared to the latent state representations that we produce. The second is a contrastive loss between, again, the ground truth latent states and our predicted latent states. And then the third one, we actually use the decoder part of our autoencoder to create a full state prediction and do a reconstructive cross-entropy loss between the ground truth state and our predicted state. We can then use these latent state representations and feed them back into replacing our state tokens. So now we've predicted what's happened in the world. We're going to feed it back into our language model so that when it describes the final state, it actually has an idea of what it's trying to describe. And in this process, we also perform the traditional causal language modeling loss so that it learns to generate language. Now, this does require a data set of text trajectory pairs. Unfortunately, these aren't readily available in literature currently, and so we decided to create 3 of our own data sets. The first is ABCDs, a bit of a throwback to Proust, where we have a robot is facing north. The robot then turns left or around, performs a series of turning actions, and the language model has to predict which way the robot is facing at the end of the sequence. The second is a cube blocking task or a block stacking task. It starts with a series of blocks in different columns. A series of stacking operations is then applied. And then the language model has to predict or generate a description describing the tallest stack in the column, which column it is, how tall that stack is, and what the column comprises of. The last one is house, and this is a data set that focuses on common household objects. And here this is broken down into a set of high-level tasks and low-level actions. So high-level tasks in this case would be something like cook an apple. And this would be broken down into the actions of the robot opens the oven, the robot picks up the apple, the robot puts the apple into the oven, the robot closes the oven, the robot turns the oven on. It then has to describe the final state of the world. In this case, the apple is now cooked, hot, and inside the oven, and the oven is now on. And using these three data sets, we wanted to answer two primary research questions. The first is if grounding language in the environment can improve the sample efficiency of the model. Inherently, we are providing more data to the model, and we would like the language model, therefore, to be able to learn faster. The second one is length generalization. Because it's able to predict the state of the world after several steps, we hypothesize that it will be able to generalize to sequences of longer lengths than is seen in training. So to do this, we first create training sets of 5 different sizes, ranging from 1024 or 2 to the 10 samples, all the way up to 262,000 or 2 to the 18 samples. All our training sets contain sequences of only 1 to 5 actions, where our evaluation sets range from 6 to 10 actions. Looking into the results, first in ABCDs, we see that Reseed does great in this data set, and text-only models really struggle. This is going to be the starkest contrast that we see, and one of the reasons we hypothesize on why this is that the ABC task is syntactically very simple. The description of the language is almost identical in every single thing, but semantically they're quite different. The actual actions happening in the world are visually more distinct. This means that it's very difficult for the text model to actually separate what's happening in the world. But we see very clearly that ABCD is able to learn at all kind of training sizes. And we also see that we also test the GPT-4 in this, and we see that giving it in context examples of, again, 1 to 5 actions, and we see that it starts struggling more and more as we generalize to longer and longer lengths. Moving on to cubes, here we actually see that they start very similarly, but as we increase more data, Reseed is able to utilize that data much more efficiently. Again, significantly outperforming the text-only model. And we see a clearer curve as well on the length generalization. And again, they start quite similarly when you're just doing a small amount of generalization, but as you extend to sequences that further and further away from the training set, the text-only model struggles more and more compared to Reseed. We see a similar trend in the house data set. Because this one is a bunch of distinct tasks and it's not the same exact action applied over and over again, the curves aren't quite as clear because there are some actions, for example, picking, that is always applies the same thing. You're always just going to end up with that object in your hand, whereas other actions like turning on the faucet are going to be very dependent on the context around it. So even though the sequences might be shorter or longer, the complexity of the actions varies. But we see overall the same kinds of trends. And we'll see that in every single case, the Reseed model is able to outperform our text-only model. Now, we did compare also, we started this whole thing saying that current language models are not very good at length generalization and sequential reasoning. So we actually tested several modern large language models on this task, including GPT-4o, and find that Reseed outperforms all of them by a pretty significant margin, especially on the cubes data set of like 65% accuracy to 9% accuracy. So the takeaway from Reseed is that text and preference data lack the rich objective signals found in the environment. These signals are essential for human language understanding and reasoning, and grounding LLMs with the data from the environment can significantly improve their sequential reasoning. This is another quick highlight supplementary paper, Eyes on the Game, Deciphering Implicit Human Signals to Infer Human Proficiency, Trust, and Intent, that was published at Roma in 2024, and is co-authored by Nicole Hull, Anthony Rees, Jake Brar, Katharina von der Mentz, and Alessandro Roncon. This switches domains to human-agent interaction, but it's the same kind of core idea. In human-human collaboration, humans rely on a lot of things like body language and eye gaze to understand things better than their teammates. Currently, most agents don't use this. So this paper really looks into how can we use these signals to predict salient information about our teammates. And indeed, we find that in the same way that humans use nonverbal signals to better understand those around them, these cues can be used by AI agents to provide similar salient information. And with that, let's move on to structure and generalization in building human-like structures. Structures, especially hierarchical ones, provide three key benefits. The first is sparsency. Because you're constraining your search space, you actually reduce the overall search space, making it easier to find a reasonable solution. Second, it can prevent inferring incorrect relationships. So if we go back to our Husky versus Wolf classifier, if we had broken down that task into background and foreground objects, creating this kind of structure, we would have prevented the model from just predicting the class based on the background. Second one is feature or component reuse, and this makes most sense with a modular skill. If you learn a modular skill in one environment, it's easy to adapt that to a new environment compared to if you just agglomerate everything into a single network. Lastly, and maybe more importantly, these structures are reusable and shareable frameworks. Now, you might be thinking deep learning structures, that's network architecture. And modern network architectures do indeed use these concepts. CNNs have these hierarchical convolutional layers, and it's been shown that layers of these different convolutional ranges pick up on different signals, with low-level features picking up things like lines or basic shapes, and higher-level features picking up like whole parts of objects, like a wheel or an eye or a beak. While less obvious in transformers, there is some work that also shows this in the several different layers of transformers. So in this example on the right, they are able to recover part of speech tagging from layers much earlier in the network compared to co-reference resolution, which depends a little bit on part of speech tagging, and those appear much later in later layers in the network. Now, there are also a lot of systems that have a combination of the two. And there are a lot of AI systems that use structures. So in the example on the left here, Seikan, they use a library of different skills, pre-trained skills, and then use an LLM combined with a value function to pick which skill to perform next. Not all of them are human defined. On this example on the right, learning interpretable skill abstractions from language, they actually just force their policy to depend on a specific embedding that is chosen from a codebook. So essentially, they first predict what skill to do, not human interpretable, just in lane space, they predict a skill, and then use that skill to condition their policy. And they show that this helps us quite a bit in low resource tasks, which is kind of supports our argument that this helps learn faster. That being said, humans do this better. This is an example from the city plan of Pearland, Texas. And it's the strategic plan for the city. And you can see that they have broken this down into many different things. But what's interesting to me is that all of these different structures have different substructures. So while the high-level structure might be breaking it down into different departments, one of the departments has broken it down into a map using a spatial structure. Also, city planning is inherently a collaborative task. And one of the reasons to have a strategic plan like this is so that everyone can be aligned in what we're trying to do. And this is what really motivated our investigation in human-agent collaboration, and specifically zero-shot coordination. Zero-shot coordination requires quickly adapting to a new teammate, and these teammates might have unknown preferences, strategies, and proficiencies. In collaborative domains, humans frequently leverage shared task abstractions to be able to work together and to anchor the collaboration in something that everyone agrees on. However, this method is underexplored when it comes to collaborating with agents. And this is where my paper, Implicitly Aligning Humans and Autonomous Agents Through Shared Task Abstraction, comes in. This was published in AMOS 2023 as an extended abstract, and recently at IJK 2025, which I'm actually presenting at next week. And is co-authored by Miguel Aroca-Ouellette, Katarina von der Mentz, and Alessandro Ronco. As mentioned, current state-of-the-art methods in human-agent interaction subsume all decision-making into a single black box. And this differs a lot from how humans approach the task. Humans rely on shared task abstractions for collaboration, and we hypothesize that providing agents with a similar kind of structure will improve their implicit alignment. So to this end, we leverage fun and develop HaHa. Fun here is feudal networks, a type of hierarchical reinforcement learning. And in this case, we separate them into workers and managers. Workers are trained to learn the movement to complete subtasks, and they focus on avoiding collisions and making sure they can get somewhere efficiently. In contrast, managers focus on which subtask to complete next, really thinking about what high-level strategy they should take on. And we first test this with other unseen agents, and we immediately see a pretty significant benefit. So we actually During this training, you train with a known amount of teammates that you train with, and we tested that with two different baselines that use different training teammates, BCP and FCP. We can see that in both cases, HaHa provides a pretty significant benefit to the performance. We also talked about how structures just generally help with generalization through things like feature reuse. So to test this, we actually we modified environments by swapping two tiles in their training layouts. And we can see here that the baselines struggle a lot with this. FCP, for example, goes from about 133 down to 9% as an average reward. In contrast, HaHa FCP only drops from 157 to 127. Now, of course, this whole thing is about humans, so we had to run a human study. And here, we can see again that these results hold up with humans. In every case, HaHa outperforms its baseline, and on three of the layouts, the three layouts that were further from human performance, got significant benefits. We also asked the human participants questions in a survey, and we found that they found HaHa to be more understandable, more intelligent, and more cooperative. HaHa, I don't believe is intelligent, but it's interesting that humans think that. So the takeaways of HaHa is that humans rely on shared task abstractions to establish common ground in collaboration. Extending this approach to autonomous agents improves generalization to unseen teammates in changing environments. And with this, let's move on to the final main section of this talk, hypothesis-driven learning and generalization, and how we test theories. So if we think about learning in deep learning, we really think about stochastic gradient descent. This enables directly learning from data with minimal human intervention, and it has predictive scaling laws, which has been very beneficial to the current boom. That being said, it requires a massive amount of data to tackle complex tasks, and it inherently requires taking small steps along a multi-dimensional loss surface. And if you take steps that are too big, you risk drastic learning instability. Lastly, it doesn't really model causality in any way. If we compare this to humans, humans from a very young age, from about 18 months, have been shown to create hypotheses. If we think about hypothesis, we also think about the scientific method, which has been formalized for centuries. And in the scientific method, we control extenuating circumstances to make causal relationships clear. And turning these causal insights better help us identify data and build useful structures as we iterate through our understanding. Now, while this is formalized a lot of times, through the experiments with children, it's been shown that humans build and test informal hypotheses about the world around them all the time. These results provide insights at a conceptual level and enables large targeted learning steps from just a handful of examples. And if these experiments are well-formed, this learning provides a cause-effect outcome, strengthening our causal understanding. And I'll do a quick tie into embodiment here. When we can act in the environment, it's much easier for us to act in a way to see the outcome of something because we are the actor ourselves. And we want to apply this to the domain of few-shot behavioral cloning. Or can we imitate a user, specifically in the context of assistive AI, right? If we want to write an email for somebody else. When we imitate a user, we want to use as little information as possible. Users aren't going to want to generate hundreds of thousands of demonstrations so that people in the model can follow theirs to be like that. Each user is also unique and out of distribution for the training data because, well, at this point, ChatGPT has seen me write a lot, but for a lot of people, that's not the case. And so to accomplish this, humans will actually infer specific attributes about the user from their behavior and then use these attributes to mimic them. And this brings us to the last main paper of this talk, aligning LLMs by predicting preferences from user writing samples. This was published at ICML 2025 and is co-authored by Natalie McGrath, Barry John Theobald, and Rin Susan Metcalf. So the motivation of the paper, as I mentioned, is to create personalizable AI agents. We want to empower the diversity in humans by creating agents that can still express the diversity that humans have. Ideally, we want to do this in as few examples as possible. And to do this effectively, we propose building hypotheses about preferences and testing them and iteratively refining them. So let's take a look at how one of the papers that we built off of did this. So we first have an article, and it would get summarized by the user using the user's true preferences. We have an agent that would do something very similar, where the agent would generate their summary. An LLM would then compare the difference of the two, infer a preference, and then directly update their list of predicted preferences the output. And a lot of this is what I'm talking about with building a hypothesis. However, what this paper does not do is test their hypothesis in any way. For this end, we propose PROSE, preference reasoning by observing and synthesizing examples. So PROSE is a method that iteratively refines and verifies the consistency of inferred preferences. And here, our inferred preferences are our hypotheses, and our iterative refinement and verification consistency are the tests that we're applying to it. So let's take a look at this again. This is what they did before, but instead of directly updating our predicted preferences, we're first going to ask our agent to regenerate the same summary using our new updated preferences. And then we can do this several times. Hopefully each time, as our preferences approaches it, more fine-grained details might come to light of what the difference is between our two writings. Although sometimes we might predict things that are way too specific to the example at hand. And this is where consistency verification comes up. In this case, we can look at previous samples we've seen from the user and check if the preferences are exhibited not only in the current one, but on previous examples as well. If they're not, we can discard them before we use the remaining to update our predicted preferences. And with this setup, we wanted to answer 3 different research questions. 1, does iterative refinement improve performance? 2, does verification consistency improve performance? And 3, is conditioning on preferences better than conditioning on demonstrations? So the de facto standard for style matching currently in LLMs is just to provide a list of demonstrations that the user has shown before. And this is what we wanted to test with the 3rd question. And we tested this on 2 tasks, assistive email writing and assistive summarization. Looking at iterative refinement, we overall found that iterative refinement provided about a 15% improvement compared to not using it. Looking at verification consistency, it was a much smaller gain, just about 1.7, but very consistent across all our benchmarks and different language models we used. That being said, this is a largely fully observable environment, and so we suspect that in partial observability environments, this verification consistency might become much more important. The next thing we did is to compare in-context learning to PROSE. And looking at the different sub-profiles that we looked at, we realized that PROSE and ICL have different strengths and weaknesses. So some of the preferences that we tested were things like write in the style of a screenplay. This is something that in-context learning did very well. It was able to see the structure and match the structure very clearly. However, in-context learning was much worse at picking up things on like intonation, like being sarcastic or being critical. And in this case, PROSE actually outperformed in-context learning. Using this insight, we realized that we could actually combine the two to do a combination of PROSE and ICL, and found that this combination outperformed all other methods. We also highlighted that inferring preferences through PROSE has a few additional advantages. The first is that users can actually see what's happening and what the model is using. This gives a lot more control to the user and a lot more transparency of why they're getting the generation they want. The second is that these preferences are much shorter than full demonstrations, so you use a lot fewer tokens at inference time. And also, these preferences have the potential to be used in a wide variety of contexts. If you're just trying to mimic somebody else, an example might be very useful. But if you're trying to collaborate with somebody else, you might want to find something to use instead. And the main takeaway for us here is that structured human-derived procedures, akin to the scientific method, can enable fast generalization to new users. So what's next, and what does the future hold? In this thesis, we've explored how to design more generalizable systems by looking at how humans use data, structures, and hypothesis-driven learning. Underpinning all of this has been a human's causal understanding of the world and our priors. However, in PROSE, we observe that LLMs are beginning to develop priors of their own about how the world works. And in PROSE, we were able to use essentially LLMs to identify data and create structures that we needed. And this is the foundation of the emergence of reasoning models we've seen. Recently, both OpenAI and DeepMind unofficially achieved gold at the International Math Olympiad. Contrary to its name, OpenAI did not release anything about how they did it. Thankfully, DeepMind did, and they released a technical report with this diagram. And we can see here that the LLM provided an initial solution. They then self-improved the solution, creating an initial hypothesis on how to solve this problem. They then went through a few series of essentially testing their hypothesis and seeing if it was working. Concurrently, there's been this line of work of actually analyzing what's happening in large language models. And I will say all this investigation isn't very, very large language models. So Anthropic did a deep analysis of Claude Sonnet 3.5, I believe, to find clusters of weights that consistently fired for specific topics. And from it, they're able to identify patterns akin to multi-step reasoning and planning a few words ahead, as well as multilingual circuits. And this is really promising for a lot of directions in the future, but there's also still a lot of limitations. They lack the multimodal experience, and there's yet to show really any true human-like understanding of language. At least I still feel like when I interact with ChatGPT, it does not use language in the same way that I use language. Maybe more practically, there are limited hypotheses and experiments in text. They can't actually interact with most of the physical world, which is very limiting. In terms of the concepts that emerge, deep, very intricate analysis was able to recover these conceptual structures. And right now, we're just at the stage of identifying these structures. We're not actually trying to target them and update them in a way to address new learning. Perhaps another step for the future is that they lack an internal world model that would allow them to plan and hypothesize about the long-term future in a stochastic world in the way that a human can. And with this, in this thesis, we explored how to design generalizable AI systems by drawing from how humans use data selection, task structuring, and hypothesis-driven learning. Here's a list of the citations of the papers presented in order. And I'd like to say a big thank you to my committee, to the members of the Hero Lab and the Nala Lab, to my family, my parents that came out here, and especially to my wife, Justine, who's supported me through all of this. And I'll open the floor to questions.
Well done. Yeah, so what I suggest is that we start with questions. So basically, anybody who has questions, like what I said for Nanya, if nobody has questions, it means it was boring. So at least one person needs to ask a question. Yeah, and then we do the committee, usually in order of distance, but also the last. So maybe order of distance at the table, and then others on the
Yeah.
Are there a lot of like situations where the biases that in your structure for these kind of systems end up performing worse? Because like I've heard things that like we don't want to necessarily include bias, but you're kind of choosing which structural bias to include based on the human's preference or like how humans work.
Absolutely. I think that's a really good point, right? But by creating structures, you are preventing connections that could be used. And if you create a bad structure, you will essentially inherently bias the system. So I think that's a big component. I guess what I argue currently is that humans are better at creating structures at AI because of a better causal understanding. And so, and the other thing is that we do this regardless of that risk. There are a lot of systems that use bad structures and that have bias in them. And I'm sure a lot of us have experienced that. But if you try to remove the structure entirely, things would probably just collapse. So I think it is something definitely to be aware of. And I think what's really important in those cases is to try and have an iterative communication with either another human or with the agent to generate these structures, right? And I think that the most important structures, that's usually the case, right? If you're creating a new company and choosing an org chart, the board has a discussion about that. It's usually not one person that on a whim decides these things, especially for larger companies, startups. Who knows what goes on that? Yeah, does that answer your question?
Yeah.
Yeah.
So you were bringing up this difference between how neural networks work through like smaller steps with that's a great extent, and then addressing this stuff humans are learning like the more conceptual level. Can you talk about like why these differences exist? Particularly, I think a lot of people in these neural networks they motivated by saying that neural networks are based on how human brains exist. So why can't they learn at the conceptual level?
That is a great question.
Stéphane,
Yes.
can you repeat the questions for the people of the Zoom?
I can definitely repeat the question. Caleb's question was, don't you induce bias by choosing the structures to use? And my answer was, you do indeed induce bias, but it's a necessary cost of using structures. And it's something that happens in human structures as well. And we don't choose to remove the structures in those human systems. Abteen's question was about the fact that I kind of talked about how we should be learning at a kind of conceptual approach and kind of talked about the limitations of stochastic gradient descent. That being said, neural networks are often kind of taught in a way that they are inspired by the neural connectivity in the human mind. And so we're talking about human inspired, and I'm talking about the limitations of neural networks and how does that kind of work together. And Actually, I was glad for that because this is something that I thought about. Yes, neural networks are great. And I don't think we should get rid of them. I think that they do provide a huge foundation, but they're just not sufficient, right? And if we look at the way that humans actually learn, and this is maybe most obvious with the way that humans have habits. At the start, when we learn habits, it's very intentional, right? There are things that we list down that we want to do to get better at things. But a lot of research has shown that as we do them more and more, we internalize these habits and they become much more automatic. And this to me is kind of a descent of going from things that are very explicit, insights that we've chosen to hold on to, and structure we decide to build, and then internalizing it through our neural pathways into something that becomes automatic. It's also been shown that these pathway connections happen a lot during sleep, which I think is very interesting. So I do think these things can play hand in hand. And there is definitely future work that could try to internalize the insights that we draw at a conceptual level and use methods like constitutional AI to then internalize those into the models without having to rely on those explicit preferences anymore. Does that answer your question?
Is it important to you that these structures be human interpretable and modifiable, or just that they exist in these systems can leverage them?
That's a really good question, and I think it depends on the context you want to apply them. Repeating the question for those. The question was, does it matter that these structures are human interpretable, or does it just matter that these structures exist? And my core argument would be, what do we want models to do? Do we want models to collaborate with humans? If we do, then we want them to be human interpretable in the same way that if I work with somebody else, I want to understand the structures that they use. Now, humans, because we have a lot of shared experience and a lot of tasks, we have this implicit shared common structure of the world. In tasks where that's not the case, though, we usually explicitly define it, right? And I think that's totally valid. We can definitely have communications with agents to determine between the two of us what structures to use, as long as we both agree to the same structure. If we just care about optimality and it's just an AI that's operating in a specific space to do a specific thing and no one's ever going to interact with it, have at it. I don't think that I think that the need for human interpretability goes down a lot. But again, if you even want oversight into it, you will need these structures. So at the end of the day, to me, in research, they don't need to be, and I actually have no issues with the AI even proposing the structures, as long as the humans can understand the structures they're using.
So this is like a silly question.
There's no silly questions.
I'm thinking of the example where you mentioned of how humans interact. The human actually has to mimic the other person's. Once they get like a structure or an embedding of what the other person's preferences are, then the human tries to mimic it, tries to basically whatever they do is trying to conform to the other person's preferences.
Yeah.
In that situation, I in real life, I rarely come across a situation where I'm only going through the text written by another person. It's a combination of what the other person's speech and then their actions in the real world, visual and text and all of these things. So the embeddings are multiple types of embeddings are combined together to give me this idea of what this person might need. So
yeah,
I'm thinking of expanding this to that aspect.
Yeah, and I think that you touched upon a lot of really interesting points that I've briefly touched upon in the presentation. The first is multimodal things, right? Humans use a lot of different signals to create the models of teammates. And I think that's really important as well. And I think that, yes, agents should do the same. I also think you talk about you're kind of iterating and updating these structures, and I think that's also super important. And it's not something I've currently done. I've kind of just been these structures, let's just start, if we give structures, that's useful. But yeah, in humans, and especially over time, updating these structures and refining these structures based on what we learn is super important. And that's a little bit what I was talking about, building new causal understanding. And that new causal understanding in turn kind of refeeds into the structures that we use. So I think both of those concepts are very important to me.
You did the question.
Oh, yes. The question overall was just kind of touching upon how when Shrikushna was basically saying when he interacts with other humans, his process is not just pick a structure, stick with that structure. He starts with an initial structure, perhaps, and then he updates that structure over time, and he incorporates a lot of different modalities when thinking about how to continue that collaboration. And so I think those are both really good points that speak to the presentation overall. Thanks.
Okay, should we move to the committee?
Yes, let's do it.
Thank you, everyone.
Fun. Wait, stay it, right?
Oh, okay. If you want to, we normally do the committee questions in a closed session, so
I'm happy either way.
it's you're right. It's all you. All right, we can do it.
Maybe
Yeah.
you
Okay.
can stay if you want to. If you don't want to stay.
Yeah, no need to stay.
I have a meeting.
Yeah, so anyone that needs to go to meetings, it's about that hour, so,
Thank you.
yeah, of course. Thanks for coming.
Okay, who's going first? It's not Alessandro.
We have to kick out everybody from the Zoom session.
Oh, yeah, I guess were there any questions from the public on Zoom? If you put it in chat, I will answer.
I had a question. This might not make the most sense because I'm not in the machine learning space. But I was curious, in some of the start of your slides, you were talking about using the text only, like ChatGPT and whatnot, for instance, like the turn left or turn east and whatnot, versus with that one post, I forget the name of your version of it. Yeah,
Yes,
it would
the
be-
ABCD data set. Like this data set, and we
Yeah.
want to, yeah.
Yeah, exactly. And then you talked about how, with the text only models, it was making a lot of mistakes. And then you talked about how with longer and longer sequences, you would expect this one to do better. I guess one question I had is that I'm interpreting that again as an amateur in the machine learning space, is that the text, whatever, I'll just say GPT here, doesn't fundamentally understand what's happening. And so if you give it, a sequence of 100 or 1,000, it starts getting more and more inaccurate. And I was curious, in your version, if it fundamentally kind of quote unquote understood it, wouldn't we expect it to not drop off so quickly as the sequence increased? At least there was a slide, it looked like it started getting worse and worse as the sequence just got a little bit longer.
Yes, it does deteriorate, just not as fast as the text only model. That's a very good question. And I've been very careful. I do not think that Reseed understands language as we do. I think that it is a step forward in that direction. So what Reseed does do is, before answering the question, it at least tries to predict the state of the world. Rather than just immediately predicting text, it's like, let's think about what the world would look like, and then that's still a far cry from how humans necessarily do this. We might actually have a full world model in our brain that runs each step by step, and then applies it. And again, I think there's a lot of, and there's probably a lot that we still don't know on how to do this. And so this is kind of like a first step towards using this environment data in a way that we can improve performance. But I agree, I think this line of research has a lot of potential in the future.
Got it. Okay, thanks.
Thank you.